morning, everyone. This side Mansi Mahindru, Assistant Professor in the Department of Computer Science. So, in continuation of the previous videos, for today, our discussion is on one very important topic of DA, that is binomial heap. One second. So, in our last videos, we have already covered what is binomial tree, what is binomial heap, what are the different properties that need to be followed in order to create binomial heap, what all operations that we can perform on binomial heap. And out of all these 7 operations, we have already covered make binomial heap, how to find minimum element from the binomial heap, and how to perform union operation on binomial heap. Now, in this session, we're going to focus on the 2 operations. That is, if we want to insert any new element in the existing binomial heap, then how we can do that. And second operation that we're going to perform is to extract the minimum element from the binomial heap. As in the previous videos, we already know how to find the minimum element from the binomial heap, but today we want to extract that minimum element from the binomial heap, and we have to fix all the violation that will definitely going to be arise when we're going to remove that element. And in the next upcoming videos, we're going to cover the remaining 2 operations, that is decrease key operation and delete operation. If you haven't watched those videos, just kindly go and watch those videos, because all those videos are the base for today's and for the upcoming session. Now, the first operation that we're going to cover today is inserting a node into a binomial heap. So, what does this operation mean? This operation is saying if we want to insert any new element into the existing binomial heap, then how are we going to do that? So here one line is written that for inserting a new node X, just create a new heap H dash. Just try to understand this particular line with the help of example. As you can see here, for example, if this is our existing binomial heap, means this head H is pointing towards 9. Means this is one existing binomial heap, and now what I want is I want to insert this 1 in this binomial heap. So it is saying that for inserting any new node X, means this node is denoted by X. For inserting a new node X, just create a new heap H dash. Means you want to create one more head H dash, and you have to point this to the new element, that is X. Just we get this particular thing till now. Okay, now let's see what else is written. And set H dash to the new node X. But how we're going to set this H dash in the existing H? How we'll do that? So here the second line says, now we can easily perform union of new heap H dash with the existing heap H. And we already know how to perform union operation. In the previous video, I have already covered this topic. If you haven't watched that video, just go and watch it once and everything will get clear. All the different cases that are basically used to resolve the violation of when we merge 2 binomial heap together are discussed there in detail. So now it is saying that you have to perform the union operation between H and H dash, right? So we're going to perform this. For that, first thing that we have to do is we want to calculate the degree of each node. Now, as we can say, there is no child node, so the degree is B0, and this particular node has 2 child nodes, so this one is having degree B2, and this particular is also having degree B0. Now, when we're going to unite these 2 binomial heaps, first we'll check, is there any binomial tree having degree B0? Yes, we have one binomial tree of the degree 0. So we'll write it here, 9. Now, there is one more binomial tree whose degree is B0. So we're going to fix it here. Now we'll check for B1. There is no binomial tree in both the binomial heaps of the degree B1. So we'll leave it. We'll check for B2, we'll get one binomial tree of the order B2, so we're going to fix it here. So it is 3, 5, 4, and we have here 12. Now, this is one binomial heap, but when we have studied the properties of binomial heap, at that time we have studied that no two binomial trees should be of the same degree in binomial heap. But here we can see this particular binomial tree is of the order B0, this one is also of the order B0, and this one is having order B2. So two trees are of the same degree. So to resolve this violation, we have to look up to those 4 cases which I have already discussed in my previous videos. So as here we can see the degree of x, this becomes my x, this becomes my next x, and this becomes sibling of next x. This becomes sibling of next x. Now as we can see, the degree of x is equals to degree of next x, but it is not equals to sibling of next x. So either case 3 or case 4 can be applied. Now for case 3 and case 4, we also have to check the keys of x and next x. So here we can see the key of x is greater than key of next x. So obviously case number 4 is appropriate for this particular scenario. So we're going to remove this x from the root node and we're going to attach it to the next x in this way. So how you're going to attach it will become 1, then it will become 9, then we have here 3, 3 is 5, and here we have 4, and here we have 12. So this is your resulting binomial heap. This is the resulting binomial heap that we're going to get after inserting 1 in this binomial heap. And still there is no violation. As you can see, this particular binomial tree is of the order B1 and this one is having order B2. So both are of different degree. So there is no violation. So we can say, yes, this is a final binomial heap that we got after inserting a node X. So in this way, you have to perform insert operation in a binomial heap. Now, if anyone asks you what is the time complexity of this particular operation, then you can say that simply what we are doing. See, we have only one node that we want to insert in the binomial heap. So first thing that we have to do is we want to set the head of the heap pointing towards the new node, that is x. So it will going to take only O of one time, right? It will take only O of one time. After that, we are performing union operation, right? And we know that union operation takes O of log n time. So the total time taken to insert any node, new node, into our existing binomial heap is O of 1 plus O of log n, that is equivalent to O of log n. Because we always take the dominating term and we neglect smaller terms. So we get the complexity as O of log n. So this is the first operation for today's session that we want to discuss. So this is the algorithm for inserting a node into a binomial heap. As you can see here, if we want to insert x in the existing binomial heap h, what we have done, we have created one more heap, head h dash, and that h dash is pointing towards the node x. And we know that when we have set head h dash and it is pointing towards this one, then there is no parent of this one, this x, right? There is no child of this node, there is no sibling of this node, and degree is also 0. Degree is 0 because there is no child node, and head h is pointing towards x, as you can see this, right? After that, what we did is we have performed the binomial heap union operation between your existing binomial heap h and the new binomial heap that you have just created with the above algorithm h dash. And after that, you have fixed all the violations and you run your operation successfully. Now, after this, the second operation that we have to perform in today's session is extracting the minimum key node. Now, before understanding this operation, it is very important to watch my previous video in which we have understand the algorithm that is basically used to find the minimum element from the binomial heap. right? And we know in binomial heap, it follows minimum heap property, min heap property. So all the minimum elements will always be present in the root node. But to find which element, which root node is the minimum, we have to run that particular algorithm to find minimum node. So just go and watch that video. And if there is any confusion, just send me in comments. Then I'll going to respond you. Now this is the procedure of extracting minimum key from the binomial heap. Now we'll discuss all these steps one by one with the help of example. This is the algorithm. We'll discuss all these steps one by one. Okay. Now, in the algorithm, the very first statement, as you can see in this slide also, the same statements I have used in the upcoming slides, but with the help of examples. So as you can see here, the first line is saying that find the root x with the minimum key in the root list of h and remove x from the root list of h. What does this statement mean? For example, if we have this binomial heap and I want to extract the minimum element from this binomial heap. So before extraction, I have to run the algorithm to find the minimum element from the binomial heap. In this video, we're not going to take that topic. So we are assuming that we already know how to find the minimum element. So we directly came to this particular point because we know 37 is greater than 10, 37 is greater than 1. 10 is greater than 1 and 1 is smaller than both the values. So 1 is the minimum element in this binomial heap. So it is saying find the root x. So we got our root x with the minimum key in the root list of h and just remove x from the root list. It is saying just remove it. Okay, so we'll remove it like this. See here. Here we have one heap. See, this becomes one heap and we have removed this particular portion here. Okay, now if we're going to remove 1 from this binomial heap, we'll extract it out, then how we're going to attach these elements in this binomial heap? Do we have to remove all these elements also? No, we can't, because only we have to extract the minimum element. Why should we extract all these elements from the binomial heap? So for that, we need to fix this part. Okay, let's see the next statement. Now the next statement is saying, just make h dash binomial heap. It is saying that you have to create another binomial heap whose head h dash is pointing towards some element. Now what are those elements? Let's see in next statement. It is saying reverse the order of the linked list of x children. First of all, we have to find out what are those x children. See, these are x children. These are your x children. So it is saying that reverse the list. What is this reverse the list? As you can see, the degree of 25 is 0, degree of 12 is 1, degree of 16 is 2, and degree of the 6 is 3. So it is saying that you have to reverse it, means so that the degree 0 will come at first position, after that degree 1, after that degree 2, and so on. So like this, it is saying that reverse the order of the linked list of x children and set h dash to point the head of the resulting list. I hope this statement is very clearer to you. It is saying that you just have to set another binomial heap head pointer, which is pointing towards the elements of the children of x in the reverse order. So what we have to do is, we have to reverse all the elements of x node and we have to set one head pointer h dash that is pointing towards 25. See, this degree is 0, this degree is 1, this degree is 2, and this degree is 3. So, and we had set one head pointer h dash, which is pointing to the degree 0 binomial tree. This much we have already done, right? Now, after this, step 4 is saying that you have to perform union operation between h and h dash. Now, what is this h and h dash? H dash is this particular part, means we have one binomial heap, h dash. Now, what is this h? This h is, see, this h is this part. Means we have to perform, again we have to perform union operation between this part and this part. Means we have to perform union operation. Now let's see how to perform the union operation in this particular case. Right. Now again we have to perform the union operation between these two binomial heaps. For that, first of all, we have to calculate the degree. So the degree of this particular binomial tree is 1. This one is having degree 2. This one is having degree 0, 1, 2, and 3. I hope till now degree calculation is very easy for you. You just have to count the number of child nodes and you can easily calculate the degree of any node, right? Now, here the degree is 1, right? Now we want to perform union operation. First of all, we have to check. See, here it will become, first of all, we have to merge these two binomial heaps. So we have to head, edge is pointing towards. First of all, we have to check whether there is any binomial tree of the order 0. Yes, we have one binomial tree. So we'll set it here, 25. After that, we'll check, is there any binomial heap of the order 1? We have two binomial tree. One is this one and one is this one. So we'll take priority to this one because we are performing union operation between h and h dash. So we'll take h first. So here we're going to write 37 and here we'll write 41. After that, there is one more binomial tree of the order B1. So we'll write 12 and here we'll write 18. Right. After that, we'll check for the degree 2. We have two binomial trees. We'll take priority to h. So we'll write here 10. Now here we have 28. Here we have 13. Here we have 77. Again, we have one more binomial tree of the order 2. So we'll write it like this, 16, 26, 23, and you have 42. After that, we'll check for the degree 3. Yes, we have one more binomial tree of the degree 3. So we'll have 6 and it has 3 child nodes, right? So this is the final binomial heap that we basically get after merging these two binomial heaps. But here we can see this one is having degree 0, this one is having 1, 1, 2, 2, and 3. So still violations are there. We have to fix all these violations. We have to take help from all our cases and we have to fix it. So we'll start from the very first case. This becomes your x. We'll take another color pen so that it will be more clearer to you. So this becomes your x. This becomes your x. This becomes your x. This becomes your sibling. Sorry, this becomes your next x. And this becomes your sibling of next x. As you can see, degree of x is not equals to degree of next x. So it means either case 1 is here, case 1 or case 2 is there, right? But here degree of x is not equals to degree of next x, means there is a case 1. And in both case 1 and case 2, we have to move our pointer ahead. So we'll move our pointer ahead. This becomes your x. This becomes your next x. And this becomes your sibling. Okay. Now, here we can see degree of x is equals to degree of next x, but it is not equals to sibling of next x. So either case 3 can be applied or case 4 can be applied. But here we can see degree of x is greater than degree of next x. So it means that case 4 is applicable for this particular scenario. So we'll apply case 4. Now when we'll apply case 4 here, then what will we get? Yeah. If we'll apply case number 4, what we'll get? Here we have, still we have 25. Now we're going to remove 37 from here. We're going to remove it from here and we'll attach it to the child node of 12. So here we have 12. Now it will become 37. Then this becomes 41. And 12 has its own child, that is 18. Now here we have 10, then we have 28, then we have 13, now we have here 77. Yeah. One more binomial tree of the order 2, 16, 26, 23, and here we have 42. Next we have one 6 and it has child nodes 3. Right. So this is our binomial heap. X is still at this particular position. This becomes your next x and this becomes your sibling. Degree of x is equals to degree of next x is equals to degree of sibling of next x. So case 2 is applicable for this scenario. You just have to move your pointer ahead. We'll take another pen to highlight it. Yeah. So in this case, we're going to move our pointer ahead. This becomes your x. Now this becomes your x. This becomes your next x. And this becomes your sibling. Right. Now we'll check. Here, degree of x is equals to degree of next x, but it is not equals to sibling of next x. So either case 3 or case 4. But here, the degree of, the key value of x is smaller than the key value of next x. So case 3 is applicable here. So we'll apply case number 3. Now when we'll apply case number 3, our binomial heap will look like this. Here we have 25. Now, here we have 12. Next we have 37. Next we have here 18. Then we have here 41. Now we're going to remove 16 from the root node and we're going to attach it as a child node of 10. So it will be 10. Here we'll attach 16. 16 has two child node 26 and we have 23 as well, and here we have 42. Next we have 10, 28. We have 77 and we have 13. Another we have 6 and it has also 3 childs. Right. Now this is our binomial heap. Still violations are there. As we can see, this one is having degree 0, this one is having 2, 3 and 3. Means we have two binomial tree of the degree 3. So we have to fix this violation also. So here we have x. Now this becomes your x, this becomes your next x, and we are assuming that this is that we are assuming that sibling of next x is not equals to next x. So here we can see degree of x is equals to degree of next x, but it is not equals to sibling of next x. So either case 3 can be applied or case number 4 can be applied. So but key of x is greater than key of next x. So we're going to remove 10 from here. Means we have to apply case number 4 again. Okay, we'll apply case number 4 again, and after that case number 4 when we'll apply, we'll remove 10 from here and we'll attach it here like this. So what is our resulting binomial heap that will get? Final binomial heap we get is this one. This one is our final binomial heap. This one is our final binomial heap. So it means that to perform all the other operations, it is very important to understand the union operation. Right? So hope it is clearer to you. Right. Thank you so much for today's session, for your patience. And we're going to be there for the upcoming videos also. We are remaining with the next two operations that we're going to cover in the next videos. Thank you so much.